Welcome back, everyone. In this video, I will be continuing the lecture for derivatives and graphs. And last time we looked at a very thorough example of just a graph and how to figure out, looking at the graph, where the local max, the local mins, the points of inflection, the intervals of all the concavity increasing and decreasing, and so on, lie. Now, what I'm going to do in the next problem is show you how to do that all with a formula. A function formula, I mean. So there's not going to be actually a formula here, but really there's two ways to do this. One way is from making sign charts. Now, sometimes this is called the first derivative test, but I'm not a big fan of that name because there is something called the second derivative test, and it has really nothing to do with the first derivative test anyway. So I just call this the sign chart method, and then we'll do this entire problem with the sign chart method. And then the next problem we'll do using the second derivative test. Now, the second derivative test only works for local extrema. So it won't tell you anything about points of inflection, concavity. It won't tell you about increasing or decreasing. It's just going to tell you whether you have a maximum, a minimum, or not even sure when the second derivative equals 0. But just want to clarify that name and why, even if you read the first derivative test somewhere, I'm just going to call it sign charts because this works for regular functions, it works for their derivatives, first derivative, it works for the second derivative, and if you wanted to go beyond that, it would work for any number of derivatives. All right, so with that, most of the functions that you'll see, since we have to do all this stuff where it's increasing, decreasing, concave up, down, local extrema, and inflection points, we're typically going to only be dealing with polynomials because if we don't, then the derivative is messy, the second derivative is messy, and then actually figuring out all this stuff becomes a nightmare. So for the most part, you'll just see polynomials. Well, the main thing is that when we're working the first two here, where the function is increasing and decreasing, we know that's related to f prime. And the first one is when f prime is greater than 0 because increasing, and the second one is when f prime is less than 0. Now I'm going to skip down here to the local extrema real quick. I think it might actually be better to zoom out a little bit for this problem. Let me see if I can go one more. That should not be too small. Doesn't look too small. The local extrema, we know that happens when the derivative equals 0. But we kind of talked about in the last video that it's where the graph changes. It has to go from increasing to decreasing or decreasing to increasing. And the best way to keep track of this, now in general that means changing sign, but the best way to keep track of this is all using a sign chart. But the idea is doing parts A, B, and E, we're going to just work with the first derivative and we don't even care about the second derivative. So let's go ahead and do that. First thing to do, compute the first derivative. So f prime of x equals, well, the derivative of xu is 3x squared minus the derivative of 3x squared is 6x minus the derivative of 9x, which is 9, plus the derivative of 7, which is 0. Okay. And now what we want to do here is we actually want to set it equal to 0. Whenever we make a sign chart for figuring out where it's increasing and decreasing, we take the derivative and we set it equal to 0. So one thing that's going to happen here is when we do this, when we set it equal to 0 and solve, when we start making this sign chart, which comes on a number line, we're just going to be able to figure out where it's positive and where it's negative without having to just formally set up an inequality. All right, so I'm just going to go ahead and solve this. If you want, just go ahead and rewrite it. 3x squared minus 6x minus 9 equals 0. So the f prime of x is not right next to it. One thing to notice is that you have a 3 in common, so you can factor it out. We get x squared minus 2x minus 3 equals 0. And hopefully you can factor this, and we can, because the two numbers that multiply -3 add to -2 will be -3 and +1. All right, so we got 3 times x minus 3 times x plus 1 equals 0. And when we set each part equal to 0, the 3 does nothing x minus 3 equals 0 gives us x equals 3, and x plus 1 equals 0 gives us x equals -1. All right, so what do we do when we make a sign chart? Well, we take whatever we're trying to make a sign chart of, set it equal to 0. So this time we're doing a sign chart of the derivative. We set it equal to 0. Actually, let me use this purple here to match this. And when you get those numbers, we just mark them off on our number line. So -1 and 3. Right. And we've actually done sign chart before. Previously, I believe it was when we did continuity, but we didn't have other functions. We just had the regular f of x. We weren't even talking about derivatives yet. So one thing I recommend when you do the sign chart is label which function you're dealing with. And this is f prime. This is the sign chart for f prime. Because when we do concavity, we're going to have to do the same idea, but we're just going to have to do it with the second derivative. So that's just something to keep in mind. But what do we do with the sign chart? Well, we plug in a number into each interval. So I'm going to mark these off in pink. Let's say -2, something to the left of -1, something between -1 and 3. I always choose 0 if I can, so I will choose that. And then I choose 4. And I plug these into f prime. So the reason I like to label it is I know I'm using f prime here. And the derivative, the f prime formula is 3x squared minus 6x minus 9. And I want to plug in -2. I want to plug in 0. And I want to plug in 4. The three numbers I chose. As long as the numbers are valid in the interval, you can pick anything to the left of -1, anything between -1 and 3, and anything to the right of 3. You're good to go. Just pick easy numbers. All right, so plug them in. We got 3 times -2 squared minus 6 times, about to put x, but we want -2. And then minus 9. And really all you care about here, you probably like getting a number, which is fine, but all we care about is whether it's positive or negative. So once you get to that point, you can just stop. -2 squared is 4 times 3 is 12. And then -6 times -2 is also positive 12. So 12 plus 12 minus 9 is positive. Now, if you want to get that absolute number, if it's 15, that's great, but we only care that it's positive. Now, what do you do on the sign chart is I don't care about what the actual number is. I just care about whether it's positive or negative, and it's positive here. So what I do is I put a plus above -2. And then I go ahead and do the same thing for 0 and 4 and figure out whether it's positive or negative and label it appropriately. So let's go ahead and do 0. We plug it into our derivative. We get 3 times 0 squared minus 6 times 0 minus 9. These all go away and it's just -9, which is less than 0. So above the 0, I put a negative. And then lastly at 4, we have 3 times 4 squared minus 6 times 4 minus 9. And let's see what we get here. 4 squared is 16 times 3 is 48. Minus 6 times 4 is 24. Minus 9. And this is 24, and 24 minus 9 is positive. So this is greater than 0. And we get a plus. Now, because these are telling you about the first derivative, this means it's increasing on this interval, decreasing in the middle one, and increasing on the right. So let me go ahead and label this. It's the whole interval it is in. So the -1 and the 3 separate our entire number line. And where the -2 is right here, all the way back to -infinity is where it's increasing. So one of the intervals it's increasing is -infinity up to -1. And is it increasing anywhere else? Well, we got it at positive at 4, which means it's increasing in that interval from 3 all the way to infinity. Positive first derivative means increasing. So we just have a comma in our other interval 3 to infinity. Now, the easiest mistake is to do all this work, do it all right, and then you just look at -2 and you have a habit of saying, oh, it's actually -infinity up to -2. So just be careful that we just chose -2 because it's in this interval. I could have chosen -100. It would have come out positive, and I would have increasing on this entire interval still from negative infinity up to -1. Now where it's decreasing, that's just where the first derivative is negative, and that's in the middle here. So it's decreasing from -1 to 3. And that takes up our whole number line. So it's not increasing or decreasing anywhere else. We have everything figured out. Now, probably the best thing about the sign chart is not only doing this, but it will also give you whether you have extrema and whether it's a max or a min. So when we go down here, I want to go ahead and answer this question because it's related to f prime. What I'd like to do is just really label increasing, decreasing a little more clearly, just what the graph looks like. So increasing means it's going up. It might be bending up, it might be flat, it might be bending down. It doesn't matter. It's just going up. It has nothing to do with the second derivative. Decreasing means it's going down. So what I'm saying here by labeling this is on this interval, it's going up. On this interval, it's going down. And then on this last interval, it's going up again. Well, think about it in your head. Go ahead and get rid of that. If we're going up and then we start going down, what's happening? Well, at x equals -1, it's going to be a local max. Why? Because it's going to be going up and then hit that point, x value, and then start going down. So we have a local max. We'll have to do a little more work here because we want the coordinates, and I'll just start with, we know the x coordinate is going to be -1. And then the local extrema can only happen where it changes sign, which means we go from increasing to decreasing or decreasing to increasing. So it's decreasing all the way along here. It's just going down. It's going down, 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 down. And then at this point, what our interval is saying here is once we hit 3, it starts going up again. So if it's going down until we get to here and then it starts going up, we have a local min. So we have a local min at this point, and it's at x equals 3. And I'm just going to leave this incomplete for the moment because the y value is on the actual graph, so we'll plug it into the original, but it doesn't have anything to do with the derivative at this point. But once again, I'll complete this. I want to do the concavity stuff, and then we'll finish up the problem by filling out the y values here. All right, now all this stuff that we did on the side here was for the first derivative, which is increasing or decreasing. It has nothing to do with parts C and D. You cannot look at the intervals where it's increasing and decreasing and know anything about concavity, because concavity has everything to do with the second derivative. So concave up is where the second derivative is positive. Concave down is where the second derivative is negative. And points of inflection, well, it's a requirement that the second derivative must equal 0, but it must also change sign. Right, so it's not a guarantee just because the second derivative equals 0 that you have a point of inflection. They might all be points of inflection, but it's all the possible ones. And we have to see where it changes sign. It's very, very similar to local max and min because local maxes and mins occur where the first derivative changes signs. If we go from increasing to increasing or decreasing to decreasing, we have neither. Because it would just be going up, up, or down, down. It wouldn't have switched the way it's going. All right, but the point here is we need to do the second derivative. And after we go through this, you'll see that really we're just going to do the same exact thing, but with the second derivative. Right, so let's go ahead and compute the second derivative. Just keep in mind the second derivative, we just do the derivative of the first derivative. So this is 6x, the derivative of 3x squared is 6x minus, derivative of 6x is 6, and the derivative of 9 is 0. So we actually don't have to do much here because our second derivative's formula is going to be so much easier. And the reason it's so much easier is, what do we want to do? You want to outline and follow the same exact steps. Once we get our second derivative, set it equal to 0 and solve this. And just for saving room, I'm not going to rewrite it. I'm just going to solve this. 6x minus 6 equals 0. Add the 6 to each side. We get 6x equals 6. And then divide by the 6 and we get x equals 1. Now, what we did is pretty much all of the stuff I did here in black. We figured out all the x values where the second derivative is 0. And once you do that, make a number line. But this time we want to make sure we're making our number line. Let me match the color here, the yellow. We make our number line with it labeled as f prime prime. So we're not doing increasing or decreasing, we're doing concavity now. We only care about the second derivative. And the one number that we got when we set it equal to 0 and solved it is 1. So it's gonna just look like that. But keep in mind, we're going to do the same exact steps, it's just with the second derivative. So go ahead and now pick a number in each interval here. So something to the left of 1, which is 0, something to the right of 1, which is 2, and plug them into your second derivative. Okay, so we want f prime prime of 0, f prime prime of 2, and our function formula is just 6x minus 6. We got 6 times 0 minus 6. Well, that's negative 6. And once again, we only care about whether it's positive or negative, so this is negative. That means I'm going to put a minus sign above the 0. Then when I plug in 2, I get 6 times 2 minus 6. Well, this is 12 minus 6, which is 6, and that's positive. But I only care about the sign here, so I'm going to put a plus. And as far as concavity goes, it's probably nice to label it like we did above. So for the interval to the left of 1, where 0 is, it's concave down. And for the interval to the right, let's see what color we haven't used. We really haven't used orange. I'll use orange. Since we got a plus here, it's concave up. Right? But as far as points of inflection, they're not as special as maxes or mins. We don't care about whether it's going from concave down or up to down. We only care that it changes concavity. So we can go ahead and pretty much label off everything here. The open interval, where it's concave up, well, we have only 1, and it starts at 1 and it goes all the way to infinity. So this is 1 comma infinity. Now the concave down was for this left side, and it's starting at negative infinity, goes all the way up to 1. And now the coordinates for the points of inflection, we have one possibility, which is that x equals 1, and it does change concavity. It changes from negative to positive, concave down to concave up. So this is a point of inflection. But once again, it doesn't matter that it's going from down to up. It could be going from up to down. It just needs to be changing signs. So this is a point of inflection. The x coordinate is 1, but the y coordinate is actually on the physical graph. So there's no reason to put the y value, at least yet, because it has nothing to do with the second derivative at this point. All right, so at this point, we've done 99% of the problem. All we have to do is complete all these local max and mins and points of inflections by putting the y value in. And the main thing about the y value that you have to remember, it's the y value of the original function because it's on the actual graph. So it's the y value of f of x. It doesn't matter if it's for local extrema or points of inflection, it's the y value of f of x. So we got the x value for each one. We will plug that into f of x to get the y value for each one of these. Okay, and let me go ahead and write the f of x down at the bottom so I can just use that. I went ahead and just paused it and wrote the f of x down here. So we don't have to scroll back up and down. But what we're going to do for each of these is just plug in the x value we figured out. Unfortunately, none of them match up, which means we have to plug in -1, 3, and 1 to get the y values. So the local max, the x value is -1, and the y value, I'll just label it so it's easier to keep track of, f of -1. Plugging it in, we get -1 cubed minus 3 times -1 squared minus 9 times -1 plus 7. And go ahead and just simplify this, but we do need the actual number because we want the actual coordinate here. This is -1 minus 3 plus 9 plus 7, and that gives us 16 minus 4 is 12. The y value for the local max is 12. Now the y value for the local min, well, we plug in x equals 3. So we got f of 3 equals 3 cubed minus 3 times 3 squared minus 9 times 3 plus 7. And this actually cancels out because this is 27 minus 27, so that's 0. And we have minus 27 from here plus 7, which is negative 20. But once again, you can just type that in your calculator. And the y value for the local min is negative 20. And then finally, the y coordinate of the point of inflection, we have to plug in x equals 1. So f of 1, I'll label this as point of inflection, y value. F of 1 equals 1 cubed minus 3 times 1 squared minus 9 times 1 plus 7. So this is 1 minus 3 minus 9 plus 7. And what does that give us? Negative 2, negative 11, negative 4. The y value is negative 4. And the coordinates, we only have one point of inflection here, and it's 1 comma negative 4. Right, so I know this was a very long problem. It's pretty much the longest type of problem in the entire course because we're doing so much. But what I want to go ahead and do pretty quickly is graph this and show you that it matches up with everything we understand about concavity and increasing and decreasing. So let me go ahead and just take my graphing calculator, and I'm going to plug in f of x, y equals x raised to the third minus 3x raised to the 2 minus 9x plus 7. And I'm going to scroll out. So let's go ahead and scroll out. The main thing is that we know we have a maximum and minimum, and actually one of each. And we can see that it works out because our local max was at x equals negative 1 and y equals 12, which is right there. Our local min was at x equals 3 and y equals negative 20, which is right there. If we look at the decreasing, we were decreasing between and increasing everywhere else, which matches up perfectly. So as far as the first derivative, everything makes sense. Now, as far as the second derivative, it's much harder to just look at a graph and tell concavity, but we know at least that around x equals negative 1, it's concave down because it's bending down. But what our formula here told us when we figured out the intervals of concave down is it's concave down all the way back from negative infinity. So as we go down into the left, it's going to stay concave down forever up until you get to x equals 1. Now, the one thing that Desmos doesn't label automatically, and I haven't found a setting that it will, is points of inflection. So you won't be able to have the point of inflection labeled, but we know it's happening somewhere between this because at x equals 1, it's concave down. At x equals 3, it's concave up, it's bending up. So somewhere in the middle is our point of inflection. And like I always say, you have to just really use your best estimate. But what we found from the formula is that it's actually at x equals 1 and y equals negative 4. So let's go ahead and just kind of zoom in a little bit. And we can see that right here, about right here, is where our point of inflection is. Once again, very hard to tell because it basically looks like a flat line if you only graph between these 2 points. So I understand that's very hard to tell, but that's why we use formulas. We don't want to rely on the graph. But I just wanted to show you that everything worked out for us exactly like we had hoped. Once again, no, this is a long problem, but now you know how to do everything with sign charts and the first and second derivative. In the next video, when we finish up the section, I will show you how to use the second derivative test. And also we'll look at a couple word problems just as far as interpreting the first and second derivative using the setup in the problem. So I'll see you there.